All right, so this is the third of three review problems that I wanted to go through. This one focuses a bit more on bonding, which is everyone's favorite topic, and one that we really haven't covered too much with these other problem sets. So first thing, we have ClO2 used as a commercial bleaching agent. It bleaches materials by oxidizing them, and in the course of these reactions, ClO2 itself is reduced. So first thing we're going to look at is drawing the Lewis-Dot structure for this. So lowest possible formal charges. Going to try to do this quick. For the ClO2, we're going to put the chlorine in the middle. We got 1, 2, 3, 4. And I'm going to preface this. It's going to look a little strange at first, but I will show you how it does work out. So there's 6 valence electrons for that oxygen. 1, 2, 3, 4, 5, 6. And then got our single bonds here, single bond there. In this case, we want oxygen at least to have the octet. The chlorine doesn't need to have the octet, but the oxygen does. So the oxygen we have on the right is good. On the left side, we're still missing one valence electron over here for the oxygen. So this is the weird part. And it's going to make some sense, you'll see. But that and that electron, we're actually going to form a double bond there. And this is allowed. This is allowed for the case of the chlorine. Chlorine is in third period, doesn't need to obey the octet rule. Both of the oxygens do have to obey the octet rule, and they currently do. So when we look at the formal charges for this, you see this does actually work out pretty good. There are other ways you could draw this out, but you're not going to get as low formal charges as these. So in the case of our oxygen on the left, the double bonded one, we can look at this. So for this oxygen, oh no, I don't want to do that. So for this oxygen, and now it's not a pen anymore. Boom. Still getting used to this. There we go. So here, why do you not work? All right, cool. So the oxygen on the left, we have 6 minus, it currently has those 2 lone pairs, so it has 4 valence electrons to itself, and there are 4 electrons locked in bonds, so 1/2 of those 4, and so we end up with 6. Take away 6 is 0. For our chlorine, normally with the 7 valence electrons, and we're just following the same process. You know, how many electrons still really belong to this? So it has 3, and again, I get this is kind of strange, but plus 1/2 is currently involved in 3 bonds, so 1/2 of 6 electrons is also 3. So 7 take away 6 gives you a formal charge of plus 1. And so overall, this is a molecule. There's no charge on it. So we gotta hope that this last case, this other oxygen on the right, we're gonna pretend that there is a G in there. There we go. 6 valence electrons to begin with. It still has 6 valence electrons surrounding it, and then the 1/2 of the 1 bond it's involved in. So we end up with a -1 there. And so this checks out. If you add all those up, our formal charges get you to 0. That's a good thing. And again, there are other ways you could technically draw this out, but it turns out that you're not going to get as low formal charges. So this is the best possible way, despite being a little bit weird. And so this kind of leads us into part B. You know, why do you think that this is going to be so readily reduced? If we think about the definition of that, you know, remember oil rig reduction is the gain of electrons. And so if you think about, you know, that chlorine, that central chlorine atom, it doesn't have, you know, there's an empty space there. There's an empty space, there's an empty spot in the orbital for another electron to join. We have just that individual electron, unpaired electron there. And so it kind of makes sense that this would readily reduce it. Chlorine's pretty electronegative. There is space for it to take an electron, so it probably will. And so that makes the most sense as far as, why this is so readily reduced. In the case of C, so in the event that it does gain an electron, we get the chloride ion, which is a lot more stable. And if we think about that, we can scroll down here. So the chloride ion, ClO2, but with that -1 charge, most of this is the same. And again, we can do the formal charges for these. The way this really works out, though, is, well, that -1 charge is that one extra electron that the chlorine now has. So we remember the formal charge on this guy was 0. The formal charge on this guy was -1. And now if we do the formal charge for the chlorine, so we have 7 minus, it has 4 valence electrons to itself, plus it is involved in 3 bonds, so half 6. And then we end up with 7, take away, well, 4 plus 3 is 7. So this checks out. We end up with an overall charge of -1, 0 plus 0 plus -1. This is a valid structure that works. So regarding the bond angle on this, I'll change color on this. Does that change the width? Yeah, it always does. I don't know why that's the case. Regarding the bond angle here, we just want to look at the actual shape. And this shape is pretty easy. So we look at this. Chlorine is our central atom. 1, 2 bonding groups. 1, 2 lone pairs. So 2 bonding. 2 lone pairs. This is going to lead to a bent shape. And, bent, similar to like tetrahedral, having like 4 electron groups surrounding it. We're going to look at maybe about 109.5, but probably slightly less. Having those lone pairs pushing on the bonds, it's probably going to get it to be a bit smaller than 109.5. What it is exactly, not sure, but probably a little bit lower than 109.5 would be safe. So that all looks good. And now, a little stoic problem as far as this case. So like looking at this, we have 15 grams of sodium chlorate, or chlorite, sorry, and then the 2 liters of chlorine gas at pressure 1.5 atmospheres, 21 degrees Celsius. How many grams of ClO2, the chlorine dioxide, can be produced? So the thing with this is you're given information here about both reactants. And anytime you're given information about both reactants, because we have information about the sodium chloride, we have information about the chlorine, this means there is going to be one of them that is limiting, and we don't know which one it's going to be. So we do unfortunately have to use both of these to solve. So what we can do is set this up. We'll do the 15 grams of NaClO2 first. I have the molar mass of this pulled up already. So for every 1 mole NaClO2, that weighs 90.44 grams. And then we look at our ratio here, so NaClO2 versus just the ClO2. And we'll include it, but you can see it's just 2 to 2. And then we look at the molar mass for the chlorine dioxide. that is 67.45 grams. Let me run this through real quick just to see how much. So 15 times 67.45 divided by 90.44 gets you 11.19 grams. ClO2. So that might be the answer. We're not sure. We need to compare this. So looking at the other information we have here, we're given all this gas information, so like pressure and volume and temperature. We want to solve a Stoich problem with this, so we should probably use that information and solve for moles. And what's nice, most of this information is already in terms of the units we need. So we have the 1.5 atmospheres, our 2-liter container. At the bottom here are 0.08206 liter atmosphere mole Kelvin. And then over here, our temperature, which is going to be 294 Kelvin. So I did convert that just in my head, 273 plus 21. So 1.5 times 2 is 3, easy enough. 0.8206 times 294. And we end up with, it is 0.124 moles, and this is of the chlorine, the Cl2 gas. So we're just about done. We just need to see how much this produces. So 0.124 moles Cl2. Start off there. And the ratio in this case, the chlorine versus the ClO2 is 1 to 2. So for every 1 mole Cl2, we get 2 moles ClO2. And again, the molar mass of the ClO2 is 67.45 grams. So we're just about up to ends here. I'll run this through real quick. And we end up with 16 rather. 16.73 grams ClO2. So this can't be it. It is too big. Our top value there, the sodium chlorate or chlorite, is going to run out first. This is our limiting. And as such, this 11.9 grams is our maximum produced. So thanks for listening. See you guys pretty soon.